In this video, we'll demonstrate the use of S1P files, including how to import and export them within DAMS Antenna Studio. First, we'll begin by explaining the file formatting for S1P files. The exclamation mark causes the line to be ignored so it can be used for commenting. The pound symbol is used to translate the formatting of the data for the program itself. In this case, it denotes that the data format is in gigahertz, that it's S parameter data, the magnitude, and that the system impedance is 50 ohms. DAMS Antenna Studio also automatically includes what the parameter actually is. It also includes the associated azimuth and elevation parameters as denoted. If the file is serving as gain parameter data of the antenna, then the export format is S21. If no measurement has been made, the default is S11 or reflection data. Two-port data can be imported into the DAMS and utilized in the simulator with measurements or with other circuit elements. When S1P or S2P files are utilized in the simulator, interpolation is necessary so that the measurement data and the S1P file have the same size and shape as well as frequency points. It's therefore necessary to always be sure that the S1P or S2P file has frequency extents equal to or outside of the range of the measurement data. When the S2P file is imported, interpolation is used to determine the frequencies necessary for the data to be the same as the measurement data. When interpolating complex data, there's a very special set of considerations. Here we see a contour of measurement data which spirals around the data points represented as asterisks. If we're going to increase the resolution of this data using linear interpolation, then the lines between the points on a complex plane are the lines which will determine where the data points should be. As shown, the complex plane is J and R, where R is the real data. The data itself is mathematically described as x plus jy. In this video, we're going to demonstrate transferring data to other CAE software, generating your own reference files such as creating reference files from measured data. We will also demonstrate how to change the frequency resolution of your data, which can be virtually increased, limited only by memory, or can be decreased as well. We'll also demonstrate with the DE726 measurement calibration file generation of S1P files for both wide and narrow frequency step. When we perform complex interpolation, it's necessary to linearly interpolate both real and imaginary data separately. The interpolation is the linear interpolation between x of n and x of n plus 1, plus the imaginary interpolation of y of n and y of n plus 1. So we're dealing with angles and phase, and there are a few things that need to be realized when doing this. One pitfall is insufficient frequency resolution, which can generate bad results. As an example, let's say we have our first data point on the minus axis, or at an angle of 180 degrees, and our second data point on the plus axis, which has an equal magnitude. This is indicative of too few frequency points. The frequency points would normally form some contour in the clockwise direction, so it's clear that the magnitude of point x in the negative direction and the magnitude of point x in the positive direction are interpolated generally. The frequency points would normally form some contour in the clockwise direction, so it's clear that the magnitude of point x in the negative direction and the magnitude of point x in the positive direction are interpolated. Generally, the answer is the same magnitude x for any frequency of the line connecting. However, in this case, point x is minus, and in the positive direction a plus, so the result is 0. So it is possible to have an error show up with complex interpolation. If error is a problem, then the measurement may not have the ability to perform complex interpolation, in which case deleting the phase is the answer to get back to standard scalar interpolation. To do that, you could use the scientific array calculator and take the data times its own conjugate and the square root, and the result is the data with no angle. A second pitfall is in a case where a measurement contour is exhibiting small resonances which have two things occur. 1, their direction shifts backwards, and 2, instead of clockwise with frequency, they're counterclockwise. That can cause an error in complex vector interpolation. If the resolution is not adequate, the point could be missed altogether. So, with a little bit of caution, one could make great use and preserve the phase in this type of interpolation. Next, we're going to demonstrate generating a lower resolution S1P file on the DAMS DE726 horn. We've loaded measurement data performed in calibration with 3 antennas. The 3 horns are calibrated 3 at a time using the 3-point method. That profile looks fairly typical for the DAMS horn. There are 1600 data points across this profile, and what we're going to demonstrate is how the labels are actually made, which include the lowest frequency of 500 MHz all the way to 20 GHz in 1 GHz steps. The first step is to realize that when exporting S1P files, Reg 0 must contain measurement data. We've previously recalled Reg 1, and we can see the data on the monitoring plot. We're going to invoke S1P mode, and we're going to export Reg 0 as an S1P file. The choices are linear or dB, and within the files there are nomenclature for which is used. We're going to choose linear in this case, and the number of digits in the file are defaulted at 6. The contents of the data file are shown. Invoking save enables us to save the data. After the file is saved, the file is automatically opened in Notepad and can be inspected. In this case, the high-resolution calibration of the DE horn results in about 12 MHz steps with 1600 data points. Next, we're going to create a calibration sticker which will have a 500 MHz data point along with a 1 through 20 GHz in steps of 1 GHz. To do this, we need to establish that frequency step, which we do through the VNA emulator and the frequency selection. In this case, because we're going from 1 to 20 GHz in 1 GHz steps, it's not possible to include the 500 MHz. So we'll employ the frequency list and create a new list. In this list, we'll put as the first frequency 500 with a capital M, M standing for megahertz. And in the second band we'll specify 1 GHz to 20 GHz in steps of 1 GHz. Capital G stands for gigahertz. When we generate the list, we see exactly the appropriate frequencies. Now we're going to generate that frequency set by doing an emulation of an ideal dipole. The measurement itself has no real meaning here. Now for safekeeping, we'll put that data into Reg 2 and re-invoke the simulator. Next, we're going to employ the interpolation icon and put it between the measurement ports. Knowing that the measurement port has the size and shape of Reg 0, we know that the emulator data is resident in the ports. While the emulator data is that of an ideal dipole, the data has no significance in this schematic. The magnitude of the ports are always zero match and 1 in actual magnitude. Next, we see that the interpolate icon is notifying us that we have no file present. If we try to run the analysis as is, we'll get an error message. So we must click the S1P S2P button to import the horn data file that we just exported by selecting the import function. We'll select ref.s1p. It's now telling us to use the interpolation icon to process the data. While we're still aware that Reg 0 contains the new frequency array, we'll calculate the new gain. Here we see the results of this process. We can see that at every 1 GHz step, an interpolated data point is generated. Down near the bottom at about half a gigahertz is the 500 MHz point. If we hold this contour and recall the original data, we can see it's very accurately interpolated. It's important to realize that the export parameter, in this case S21, is the parameter associated with the monitor plot. So if the monitor plot has a different parameter such as S11 or antenna factor, then that parameter is included in the export. In that way, when the file is imported, the S matrix of the icon can be easily established, which in this case is S21, S12. If it had been an S2P file, then there would be 4 parameters here. So it's very important to have the dataset labeled properly in the monitor plot, and it's set from whatever is calculated. Now that we have the 1 GHz data, we're going to create a calibration file for that. We'll invoke the export Reg 0 as an S1P file, and that S1P file will take on the attribute of S21. In this case, we're going to go in dB so it can be picked up later by the import ref antenna. Again, 6 digits is the standard, and we see the file in dB ranging from a high of 20 to a low of 3. We'll go ahead and save that file as cal file, and here's the actual file. We see the frequency range is 0.5 to 20 GHz with an unequal number of steps. The export file is S21. The slider setting on the array calculator was azimuth 0 and elevation 0. Next, we're going to create a calibration file which requires exactly 10 MHz steps over the entire band. This is an interpolation process where the desired result has a greater number of points than the actual data did. To do this, we'll return to the measurement section and we'll use the frequency list, and we'll edit instead of the single frequency. We'll just go with the band 500 MHz to 20 GHz in steps of 10 MHz. When we generate that list, we see that we're going to have a fairly large file. We'll go ahead and generate the frequency array with the VNA emulator and re-invoke the simulator. At this point, we've done nothing more than to change the frequency resolution using the emulator. With that frequency resolution in Reg 0 and the calibration file loaded, we're now going to go ahead and calculate the new gain with 10 MHz steps. We see we have essentially the same profile, just more data points. We'll store this data in Reg 2. Now, in Reg 3 we have the low resolution cal, in Reg 2 we have the high resolution cal, and in Reg 1 we have the actual measurement data. We're going to export the high resolution data as a linear file, and we see that the steps are exactly 10 MHz. So this is an effective way to create your own calibration on your own antennas and make them available to your measurements. Next, we'll overlay all 3 plots: the original data, the 10 MHz steps data, and the linear data. We can now see that the interpolation has been done properly. The file icon can also be used in any array of networks or circuits, provided that the extents of the frequency and the interpolated file exceeds that of the measurement file. And this concludes our presentation on S1P and S2P files. We hope this sheds some light on the full capabilities of these type of files. If you have any questions or comments, please feel free to use the information on your screen to give us a call or send us an email. Thanks for watching.